Hopefully you're now somewhat familiar with finding the derivative of a function, what a derivative means. What we're going to be looking at today is something that's called differentiability. When we take the derivative of something, of a function, it is called the process of differentiation. So differentiability is just the ability or lack of ability to be able to take the derivative. So differentiability would be the ability to take the derivative. So I would say that a function is differentiable if I can take the derivative. What we'll be doing by the end of this lesson is being able to use the properties of derivatives to find where a function does and does not have a derivative. Okay, so we're just going to look at some cases. When does a derivative not exist? The first case, we have the absolute value function. Please notice that there is a sharp turn at x equals 0. So if there is a sharp turn at a point on a function, at that sharp turn, there is not going to be a derivative, and this would be called a sharp turn. Some books refer to that as a corner. So if we have a corner or sharp turn, it would not be differentiable at that point. Okay, this next example, we once again have a sharp turn, so we know at sharp turns we cannot take the derivative, so at x equals 0 again, this function would not be differentiable. And this actually, when it curves and comes to a point like that, it's actually called a cusp. So at a cusp, the derivative does not exist. And then we have two more cases. Actually, I'm going to draw one more as well. If we have a graph that looks like this, notice at x equals 0, once again, this is not going to be differentiable, because if I were to draw the tangent line at this spot, we would have a vertical tangent line, and the slope of a vertical line is undefined. So at x equals 0, if we have any vertical tangent lines, there will be no derivative at that x value. Okay, and then another case is wherever, notice again at x equals 0, this function is not going to be differentiable. This function is not continuous, so at points of discontinuity, there would be no derivative. In another case of looking at points of discontinuity, if I had, let's say, we'll keep it at x equals 0, if I had something that looked like this, again, at x equals 0, there would be no derivative, because there is a point of discontinuity at x equals 0. There's actually a vertical asymptote, and it is definitely, the graph is definitely discontinuous there. So those would be the cases where we are not going to have a derivative. All right. One theorem that we're going to look at, if f does have a derivative x equals c, then it must be continuous. So that's, we're just following. So if a graph is not continuous, then it can't have a derivative. Just backing up. What we're going to look at in our examples are finding places where f is differentiable. So we might want to first of all write down where it is not differentiable, and then we'll write down where it is. So I'm going to start with example A. Where is it not differentiable? So where are there either discontinuities, vertical tangent lines, or sharp turns? I notice that at -3, at x equals -3, and at x equals 3, we have some cusps. So we know that it is not differentiable at x equals -3 and x equals 3. At x equals 0, we're fine. It has a horizontal tangent line, and that's fine because the slope of a horizontal line is 0. So that one is not an issue. So when it says describe the x values at which it is differentiable, kind of like when you're writing the domain, it is differentiable from -infinity till I get to -3. It's not differentiable at -3, so I'm going to keep that as in a parenthesis instead of a bracket. And then it is differentiable between -3 and 3, and then it is also differentiable from 3 to infinity. And again, notice I'm not including -3 and 3 in my intervals. All right, part B. Again, let's find out where it is not. And if I look at this graph, any place where the function would be discontinuous, we know that it's not going to be differentiable. So at x equals -2 and at x equals 2, this function is not continuous, but it is differentiable everywhere else. Everything else looks real nice and nice smooth curves, no sharp turns or cusps or corners. So it is differentiable from -infinity till I get to -2, then between -2 and 2, and then from 2 to infinity. Okay, so notice that on this one, this pretty much describes the domain. This one didn't describe the domain because it is continuous. We just have sharp turns. Okay, and then C, we have another spot of discontinuity, which would be at x equals 1. So at x equals 1, we would not be able to take the derivative. So let's say where we would be able to take the derivative, we can take it everywhere else. So from -infinity till I get to 1, and then from 1 to infinity. So that's where we should be able to find where a function is differentiable. So hopefully now you can tell where a derivative exists or does not.